Now we're going to put all the elements together and look at the driven series RLC circuit. And what we mean by that is simply we have an oscillating drive. It goes to a resistor and a capacitor and an inductor all in series. Okay, we're going to apply that delta V is going to be our standard delta V max, our amplitude of oscillation, sine omega t. And we're really just going to quote the result. From here, it's pretty complicated and a little bit beyond freshman physics. What we would do is set up the sum of all our potentials and get a differential equation similar to when we solved the RLC circuit without the drive, when we just saw that damped oscillation. It'd be similar to that, except instead of being equal to 0, it would be equal to the drive potential. So there's ways to solve that in differential equations. We aren't going to do it now. I'm just going to tell you the result. But I think this will help you. We'll understand the result. And you'll see it 3 times in your life if you keep studying physics and math. You'll see it when you study a driven damped harmonic oscillator, the exact same equations. You get that differential equation, you have to solve it. And you'll see it when you study these in more detail someday, RLC circuits. And if you take differential equations, the same differential equation in class will show up in the 2 physics topics. So you'll see it, I promise. Right now, let me just tell you that this will lead to a current, an oscillating current, I max sine omega t, and it's going to be some phase lag, minus phi. Okay? So if you drive it at omega, it will eventually oscillate at omega. That's part of the process of finding the answer. And there will be, we talked about in each one of the elements, it's in phase or it leads or it lags, the current and the voltage. Here, you're going to end up with a phase difference of some amount. It won't necessarily be 0 plus or minus pi over 2. It'll just be some amount. And since they're in series, all elements have the same current at some point in time. If you go make other more complicated RLC circuits where you put maybe 2 of them in parallel next to one in series, then that changes the answer. Here we're just doing it for when they all have the same current. So the big question is, what is this and what is that? So the maximum current you get will indeed depend on the value of R, C, and L, and on omega. And let's see, I max will be proportional to delta V max, as you would expect. If we were just across a resistor, it would just be the resistance in the bottom. If it were across one of these individually, it was just the 2 reactances. So really, when they're all 3 there, it's a combination of those 3. It's the square root of R squared plus XL, the inductive reactance, minus the capacitive reactance squared. And this altogether is called the impedance of the circuit. The impedance is kind of like the generalized AC resistance that you would just think about in a normal DC circuit. So that's how you combine the three elements, or that's how you combine their resistances and reactances. The phase lag that you get also depends on those 3 things. It's the inverse tangent of, no, let me get it wrong. Yes, XL minus XC, yes. This minus this over R. Again, if we went through, guessed the differential equation solution, solved it, plugged in the constants, et cetera, you end up getting something like this. And this shows you, since it's an inverse tangent, basically it's only got unique values from plus pi over 2 through 0 to minus pi over 2. So that's where your phase is always in there somewhere. If you want to know what's going on in each individual element, I'll just draw it again real quick. The capacitor you use that current. So say you want to know what is the voltage drop across the resistor. Well, you say delta V R, so a capital V there means that's the maximum value. That's the delta V max over the resistor. Well, it's equal to IR. So you take that formula I gave you for I max and you just multiply it by that one's resistance, and there's the delta V, the voltage across the resistor, because the voltage won't be the same, right? That's got to be divided up between the three. The capacitor, delta V across the capacitor. Well, now you can use the generalized Ohm's law. V equals IR. Well, V equals I max, that amplitude, times the impedance, or times the capacitive reactance, the capacitive part of the impedance. So that's I max times XC, but that's basically equal to I max over omega C, because the capacitive reactance was 1 over omega times C. So you can see as the capacitance gets, as the frequency gets higher, the voltage drop across the capacitor will get smaller. That's because at higher frequencies, capacitors basically act like a wire. As the frequency goes way down, delta V, the voltage drop across the capacitor will get really big, because at low frequencies, the capacitor is basically a broken circuit. Okay? So it sort of makes sense. And finally, you go to the inductor. Same thing. Ohm's law generalized for an AC circuit, more or less, I max times the inductive reactance, which is just I max that I gave you before, times omega L. And there, the inductor is the opposite of the capacitor. At high frequency, you're changing this magnetic field really fast, a lot of induction, therefore a big voltage drop across the inductor. So with these, right off the bat, figuring out the current and the phase, if you want to know the phase, and then with these, you can get the amplitude of the current across each element. You can also get the amplitude of the voltage across each element. Now that we know a little bit about RLC circuits, let's look at an RLC condition called resonance. So RCL, and recall that we looked at it before we were driving it, and we solved the differential equations for what would happen in time, and we looked at the current. Remember, it would oscillate and decay. It had this natural frequency which it wanted to oscillate. But then the resistor would cause the decay. It wouldn't oscillate forever. So we kind of looked at that. Now if we drive it, the differential equations lead to something kind of similar. It does have a frequency where it really wants to oscillate. So if we go back and look, I max, the maximum, or the amplitude of the current oscillation, was V max over the impedance, the square root R squared plus XL minus XC squared. So you can look at this and say, well, I want the current, what's it going to be? It's going to be V over something. And you realize there's something special when these two are equal. Not that they're zero. You don't have to get rid of the capacitor and the inductor. Just when they have just the right value that they're equal, what's going to happen is, when that happens, then that's going to be 0. And when that's 0, that's the smallest value you're going to get in the denominator. Therefore, it's the biggest current you're going to get. And if the resistance happens to be small, then you're going to get a really, really big current because you get your Vmax over something small. But the maximum you're going to get is when those are equal. Let's see what that looks like. That's when omega L equals 1 over omega C. So you bring that over here and that over there, and you get that happens when omega squared is 1 over LC, or when omega is the square root of 1 over LC. Which you may recall, that was the frequency where this happens. That's the natural frequency. We call that omega naught usually. That's the natural frequency where this circuit sort of wants to oscillate. If you just perturb it and just let it go, it'll oscillate at that frequency. What's also true, if you drive it at that frequency, you'll get your biggest response. this is called a resonance. If we were to plot the amplitude you would get, and amplitude could be many things. You could plot power or voltage across one element or whatever. Here we could just plot Imax, right, the maximum current. Then it looks something like this. It goes through a peak, and it goes through that peak at omega naught if we're plotting versus omega. Okay. Omega naught is the resonance frequency where you get the highest current. So resonances are interesting. They can be really sharp or they can be not so sharp. The center, the position of the resonance, omega naught, depends on L and C. The width of the resonance, how sharp it is, depends on the losses. It depends on R. So the lower your resistance, the sharper the resonance you'll get. Here's another AC circuit you might find interesting, and that is the RC filter. So we talked about RC circuits before, and we mostly were talking about charging and discharging them. We just had a DC battery here, and we had a switch. I guess that was the good part. But now we are going to drive it with an AC source and see what this circuit can do. All right, so what we're going to think about is how could this act as a filter when we look at the voltage across the capacitor, delta VC, and the voltage across the resistor, delta VR. And this is oscillating, but I'll again just write delta V max. We'll say delta V max is the input amplitude that you're giving everything, sinusoidal oscillation with an amplitude delta V max. What amplitude do you get across the resistor, and what do you get across the capacitor? That's the question. So to start, we just use our generalized result for any series RLC circuit, and that is the current max. The amplitude of the current is delta V that we apply over the impedance, over the square root of R squared plus the inductive reactance minus the capacitive reactance squared. Okay, so that's the current that will flow through the circuit for any frequency, and then we quickly say, oh, actually there is no inductor in this circuit. That simplifies things. It doesn't have an inductor. So we could rewrite it then as delta V max over the square root of R squared plus, and then you can see it's just XC squared. It's just the inductive or the capacitive reactance squared, which we can go ahead and substitute 1 over omega C. There we go. So that's the current. Now, we want to know what's happening on the capacitor. So what's the voltage drop across the capacitor look like? Well, we can just use our generalized V equals IR for an AC component. So delta V, the amplitude across the capacitor, is the current over the square root of R squared plus 1 over omega C squared times R, but in this case R is the generalized version. It's the capacitive reactance times XC. All right. And what were we trying to solve for? We were trying to figure out how much of the input signal, which might be some complicated mess, how much of it comes out over the capacitor, or at some frequency, what fraction of the voltage comes out over the capacitor. So we want delta VC over delta V max. To get that fraction. So you can see it's 1 over the square root of R squared plus 1 over, I'll write, omega squared C squared times 1 over omega C. And then we just distribute that omega C onto the R squared and C squared, and you can see what's going to happen. We're going to get 1 over the square root of, this goes in, it becomes omega squared C squared of R squared omega squared C squared, and then here it comes in and cancels, plus 1. So that is what you could call the transmissivity. That's how much of the voltage you get across the capacitor divided by the original voltage that you put in. And you can see it's a function of the resistance and the capacitance in the circuit, but it's also a function of frequency, as we would probably expect. So now I'm going to plot the ratio delta V over delta V max. And here's 1 and here's 0 for different frequencies. Okay? So for this capacitor, if delta V, we mean delta VC over delta V max, at very low frequency, this is 0. Okay? This is 0. This is 1. 1 over 1 is 1. So very low frequencies, all the voltage drop is across the capacitor, which you would expect, because at very low frequencies, a capacitor is an open circuit. So all the voltage drop will be there. There'll be no current, no voltage drop here. But then at very high frequencies, this becomes infinity. This becomes really large. This is meaningless. This is something big. 1 over something big is 0. So we're heading towards 0 as a 1 over r function. So it kind of does something like this. Okay. So at low frequencies, you get a lot of the voltage drop across the capacitor. High frequencies, it goes away. So this is why it's a low-pass filter. So this is the capacitor. Because low frequencies will show up here and higher frequencies won't. What I'm going to do is demonstrate this for you with an audio demonstration. So here I've got a microphone. I'm going to talk into the mic, and you're going to hear the sound coming out of the amplifier. So here we go. So here you can hear I am sending in a signal at a bunch of different frequencies. It's going as an electrical signal and coming out of the amp. Let me show you what that looks like, just to make sure we're all together. So if I'm standing here and I've got the mic like that, and I talk, I'm sending an oscillating signal. So I'm going from sound, and the mic is converting it to electrical. This little v is this oscillating voltage we've been talking about. So that's what the microphone does. It does it with Faraday's law of induction, by the way. A little diaphragm moves a magnet near a coil of wire. That signal is sent along a wire in this unbalanced cable, but the wire has the line going down the middle, plus it has a ground braid. So there's sort of two wires to think about. There's also the ground braid in the cable like this. Two wires. This one is basically grounded. I think it was grounded. This one actually has the signal in volts. And those come back together inside the amp, and Faraday's law of induction again moves the diaphragm and makes sound. So then it goes from it goes from voltage back to sound. And it's amplified. That's the whole point. Right? Okay, so, but having it as an electrical signal gives us a chance to mess around with it. Okay? So we're going to make an RC filter. We're not going to analyze it mathematically at that level of detail and with a real circuit diagram, but it is going to be RC because we're going to put a capacitor basically right here. Okay? We're going to put a capacitor between the signal and the ground line, and the resistor is here. Okay? So there is an R on this side. It's the amplifier has some effective resistance. It actually has impedance because it has inductance, and it's a big complicated mess, but it's roughly like the resistor, and if we calculate its impedance, we can calculate what value of the capacitance will make it cut off somewhere in the audio range where you can hear, where our voices are. Because we can hear and we speak in the range from about 20 hertz to about 20,000 hertz. So I've chosen a capacitor that will cut off somewhere in the middle of that range. I did that, by the way, by looking at about here. So the cutoff frequency is somewhere in the middle of this curve where it's kind of halfway down, and it's roughly equal to 1 over RC. If you want that frequency. If you want it in hertz, it's 1 over 2 pi RC is about where you would want to put it. Okay? So I've got a capacitor that does that. So what's going to happen is you can think about whether this is high pass or low pass. Just think about a capacitor. Okay? At high frequencies, it's basically a wire. So high frequencies are going to come, and they are going to see this capacitor and go right through it because it offers essentially no impedance to them, no resistance. Low frequencies, and so they're going to go to ground, and they're lost. They aren't going to make it over here. They're shorted to ground. Low frequencies, to low frequency, the capacitor is basically an open circuit. It doesn't see the ground wire, and it just keeps going, and the low frequency makes it to the amplifier. So by putting a capacitor right there, we're creating a low-pass filter. So here we are. I've taken the cable and cut it open, and I've exposed the ground braid is on this side, and the actual signal wire is on that side. So let me get it back on and start to speak into it. And now you can kind of hear my voice that you've had to listen to for 9 weeks. And I first want to give you an idea of what it's going to sound like when we give it a low-pass filter effect. Right now, this is just sort of normal sound, but I can turn up the bass on this amplifier. It has its own low-pass filter built into it. So if I turn the bass up, you can hear a change in the quality of the sound. A lot of the hissy, high-frequency parts are gone. Now it's more smooth, more of the lower parts of my voice, and then I turn it back off, and then you're back to the normal voice. So what I'm going to do is drop this capacitor in. It should act like a low-pass filter, and we should see the exact same thing. So here we're going to touch across there, and let's see, we touch across there, and sure enough, just like turning up the bass. So a lot of the high frequencies in my voice are going through the capacitor to ground. Everything else, the low frequencies are getting through. When I take it off, you can see the difference. Blah, 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 high frequencies, and then I take it off. And I promise I'm not changing my voice. It's just the filter. And it really, I like the sound of it. It's kind of, old man river, that old man river, it must know. Okay, anyway, enough of that. There's many times when you would want to use an RC filter, and there was even one in an earlier demo. If you look closely, when I turned the generator, the old-fashioned generator, if you looked at the scope, this actual capacitor was across the leads going into the scope. Because those old generators make a lot of noise. There's a very spiky signal coming out of those things from the brushes touching the spinning part. So I had this capacitor in there to, again, low pass and just show me the part of the signal I wanted to see. So if you work in electronics at all, this is one of the most fundamental circuits. I guarantee you will play with RC filters.